Hi guys, so in our last video we talked about the vectors and the scalars. Then I was also introducing my course. So in today's video we're going to get to the actual business actually. So we're still going to do some concepts that we covered in grade 10 and grade 11. Then after covering those concepts is where we're going to deal with the grade 12 start. So now actually just doing the revision of what we did in grade 11 and also in grade 10. So one of them is mass. You have to understand mass. So mass actually just the amount of matter in a body. So this is a amount of matter in a body. So that when we're talking about the mass, actually we're just talking about the amount of matter that the body has. Then you don't have to confuse a mass with an inertia, because they can ask you sometimes to define inertia. So don't ever confuse the mass with inertia. So inertia and mass, they have the same SI units, but they're not the same. So inertia is going to be the tendency of an object to resist a motion. I will just resist a motion. I don't have a space. Resist a motion. So the tendency of any object to resist any motion. Let's say here we have a kid. We have a 2 years kid, and then this 2 years kid is trying to lift a box. So this 2 years kid can't lift that box. Then that's because of inertia. So it's because the box is resisting the motion. So that means that the tendency to resist a motion, that's an inertia. And then the mass is amount of matter in a body. So the SI unit that we are going to use in physics, it's kg. The units, SI units, it's going to be kg. So we're going to use a kg to represent the mass. So let's do this one, the velocity. So velocity, any object that it's moving, that means has a velocity. As long, even you, if you are moving, that means you have a velocity. So a velocity, how can we define a velocity? So here actually the velocity that we are going to talk about is not just a velocity. We're going to talk about the average velocity. Most of the time we're going to talk about the average velocity, or constant velocity. So an average velocity in this time is going to be the change in displacement over time. So this is just the change in displacement, change in displacement. And you remember the displacement from grade 10 and 11, changing, I wrote distance instead of displacement over time. So therefore that means the formula for velocity and the symbol for mass, remember I didn't write that, forgot. The symbol for mass is going to be m. So m, which is going to be measured in kg. Let's say just say 1 kg. So that's going to be a mass. So the velocity here, so we're also going to have the what is this, the symbol for velocity, and determine whether the velocity is a scale or a vector. So since in our last video we did these things of a vector and scale, and then we talked about the mass in our last video. So velocity is going to be a vector. That means a velocity has a direction. So this the vector and has an SI units of meter per second squared. And then it's calculated the V average that we are talking about, the change in V, which is a V average, is going to be the change in displacement over the change in time. This is the formula that we are going to use. And let's go to acceleration. So acceleration is the same as velocity, but this time we're talking about the acceleration. If we're saying that an object is accelerating, let me just show you an example. So let's just do one example. for acceleration, the concept of acceleration. So acceleration. So let's say you have two cars here. Here you have a truck, and then here you have a Lamborghini. So I'll just write L as for, which stands for Lambo. And then here you have a start line, about to race. So this is a start line. So this is the finish line here. This is the finish line. So the speed, let's say the maximum speed of Lamborghini is 320 kilometer per hour, and the maximum speed of this truck is 18 kilometer per hour. So since we're telling the driver for Lamborghini that the driver for truck can reach a maximum speed of 108 per hour, so your maximum speed of this Lambo now, that means the driver of a Lambo doesn't have to exceed 108 kilometer per hour. So this is going to be also the maximum of Lambo when they're racing. But guess what is going to happen? When they start racing, this Lambo is going to take 5 seconds, or let's just say 10 seconds. It's going to take 10 seconds. They're already here, midpoint. So the Lambo, when they're here, the Lambo has a speed of 180 kilometer per hour. And when they started, both of them, the speed was 0. So here, this is the speed at this point. But the truck here at this point, still it's moving with 60. It's moving with 60 kilometer per hour. 60 kilometer per hour. So what's the difference? Both of them, they took 10 seconds to change the speed, but the Lambo changed the speed faster than truck. So that is acceleration. So that means the Lambo has a higher acceleration than the truck. So what's the acceleration actually? Because the speed initial was 0 and then now it's 108. And then what the time taken to reach that speed? 10 seconds. So we can just simply say that the acceleration actually is just the change in velocity over time, because this, since it has a high acceleration, that means it can accelerate fast. It can reach 108 faster. This one can reach, it's gonna reach 108 one. This one is already at 320. So that's a concept of acceleration. So you can see that acceleration is just the change in velocity over time. You can write that by your own. Change in velocity over time. Change in velocity over time. So you can guess the equation for acceleration already, because it's the change in velocity over time. So it's gonna be just the change in velocity over time, over change in time. So since velocity is a vector, so what's going to be for this acceleration? Also acceleration is going to be a vector. So acceleration, it's a vector also. It's a vector. So it's not necessary that the acceleration points in the same direction as a velocity. If acceleration and a velocity, they point in the same direction, if this car is going this way and then at the same time it's accelerating, that means the speed is going to increase. So if it's accelerating, if the displacement is going this way and then acceleration is increasing, therefore the change in speed is going to increase. The speed is going to be high. But if the object is going this way, this is the object, it's going this way, but acceleration, let's say displacement of this object, the change in displacement is still going this way. No, it's going this way. You are pressing the brake. So when you press the brake, actually you are reducing. Remember that the displacement is x final minus x initial. So if you started here and then we say that from here's a 0 point, then when you go to this side it's positive, when you go to this side it's negative. So when you are going this side but you're decreasing the speed, what's happening? You are slowing down. So when you slow down, that means the acceleration points in opposite direction. Acceleration, when you slow down while you're going this way, acceleration is going to point in this direction. But velocity is still going to point in this direction. So when they point in opposite direction, just know that the car is deaccelerating. So after covering those concepts, now we're going to move to Newton's law. And remember, keep track of those concepts. They are very useful when we're going to do momentum and energy, all of those things. So here in grade 12 you are going to need those concepts. You're going to need them. So now let's do Newton's law. It's also a revision of what we did in grade 11 and in grade 10. So we start with the Newton first law. Let's say here you have an object. You have an object here. You have this big object. We call that object B. Then you just place a small box here. We call that object A. And then you just lift this object. You just lift this object B upwards. You are here. And then what you're doing, you are lifting this object up. So you're trying to lift it up. So when you lift it up, it comes to an incline of this. So now it's at an incline, it's still B, and then that object A is here, but it's still there. So object A is still here, object B is here. So what's causing the object A when you lift this to not slide off, but when you lift it again, at some point it's gonna start sliding down. So initially when you lift this up, the object doesn't fall down immediately, but when you lift it up and lift it up and lift it up, it's gonna start to slide down. So that is because we have a net force that's acting on this object A. What's that force? It's a friction. You learned that in grade 11. So that means that net force is the one that caused the object not to move. So if in the absence of air friction, or in the absence of a net force, the object will continue moving in the same direction unless there's a net force acting upon the object. So just that's a Newton first law. Object will continue moving unless we have a net force. So this object will stay here or will slide down up until, only if we have a net force acting. Only if we have a net force acting. Have net force acting upon the object. So the law, Newton first law, actually here we're just doing a revision. We're not going to state these laws. You already know them. So here we're going to second law. So second law states that if you have an object here, you have an object B. Let's say this is object B, and then now you're here. And then what you're doing, you're just pushing this object. You're pushing it up. You are pushing this to this direction. This object will move in that direction. So that means if the net force is acting on an object, the object will move in the direction of a net force. This is a net force. This is a net force. So that means if you are applying a force here to this side, therefore the object will move to that side. So it's where this formula came out. Net force is equals to ma, if you still remember, which A stands for acceleration and m stands for the mass. So we know the SI unit for this one, for force. SI unit for force is Newton. SI units Newton is N Newton. So that's a Newton second law. If you are applying a force on an object, the object will move in the direction of that net force. And also you have to know that the net force is directly proportional to the acceleration and inversely proportional to the mass. Or you can just say acceleration is directly proportional to the net force and inversely proportional to the mass. Let's check that relationship. If you can take this, you can see that here in physics or in maths, when we're saying things are directly proportional, it's when they're related in this form, in this linear form by equal sign. So here we have F net is equals to m times a. So I can say F net is directly proportional to the mass and is directly proportional to a. Or I can say F net is directly proportional to the product of mass and acceleration. So simple, we're just saying that F net is directly proportional to acceleration, you can see. But this acceleration, it's inversely proportional to the mass. Acceleration is inversely proportional to the mass. Because if we make acceleration the subject of formula, we're going to get this. Let's say now acceleration is the subject, so we're going to get A, which is equals to F net, and then divide by M, because you take M to this side, therefore we're going to divide both sides by M. So A is going to be F net divided by M. So you can see that this is inversely proportional to this. They're like this, they're not aligned, or they're not facing each other. Yeah, so let's move on. So now we're going to just do Newton third law and universal gravitation. So third law states that if you have an object here, an object A, and then here you have an object B, so that means force A exert a force on a body. If body A exert a force on a body B, also body B will exert the same force but in opposite direction. So if I push this with 10 Newton, and then this A, F of A now to B, F of A to B is 10 Newton, because this F of A is exerted on force of B. So F of B on A is gonna be minus 10 Newton, because it's in opposite direction, and we said that the force is a vector. So if this A is pushing this B, also the B is pushing the A with the same force of minus 10, but the of A is gonna be positive. So that's a Newton third law, which is called actual action-reaction pairs force sometimes. So we are going to universal gravitation. So this one, it's where we're talking about the space objects, actually the objects in a space. So each and every object in a space, they attract each other. We have a force of attraction. So let's say this is a Mars, this is a moon, and then this is sun. So sun attract the Mars, while the Mars attract the moon. They also attract each other. With a force that's directly proportional to the product of their mass and inversely proportional to the square distance between their centers. You still remember the law. So the formula that we're using here is F is equals to G M1, which is a mass 1, mass 2, divided by R squared, which R squared is a distance of between two objects from their centers. Let's say this object 1 and then this object 2. So when they attract each other, we're counting this distance from the center, not from here, from the center as R, and also from the center as R. Then we're taking this M1, then this M2. So the force that relates them is this one. So this is the force that relates these two objects. So that's a force of attraction. This is a universal force of attraction. Then here we have a gravitational constant, which is always given, that gravitational constant. So let's move on to conservation of energy. So the conservation of energy just states that if energy cannot be created, or energy can be destroyed, can be created, or destroyed, can only be transferred from one object to another. So that's a conservation of energy, and also states that in an isolated system, an isolated system is a system where, like, I will even cover that in this video. Isolated system. So I want you to understand what's a system first before we can talk about this one. So a system actually just a group of objects, or one object or more that we can separate in our minds. So let's say now we have these objects here, you have these objects, you have all of these that attract each other. Remember that, as we stated here, that each and every object attract each other if they have a mass. So these objects, if you want a system, you can just say these objects here, this one and this one and this one and this one, are system. So is this system isolated? It can only be isolated if we have no effect in these objects that's coming outside of what we didn't include in here. So if this object here caused this one to move to any direction, then now we're talking about the net force of this. We're talking about the net force. This system is not isolated. Why is not isolated? Because there's an external force that's coming outside the system and attract this object. Also another external force that's coming outside the system and attract the object. So if the system is isolated, it's where no external force are coming in. For example, when the object is falling downwards, it's falling with a 9.8 meter per second. This is the gravitational acceleration. In grade 9 is there, grade 10 is there. So it's falling with a 9.8. It's falling downwards. So here, let's say this is a ground. And then now I'm saying I want to choose a system. So if I choose a system, that means my system has to include the ground. So I say this is my system. So what's in my system? My system is a earth. My system consists of earth and the ball. So since my system consists of earth and the ball, that means what's the force that it's causing the object to fall? It's a gravitational attraction force. So that's it's this force here, weight, that's causing this object. And then that's not coming outside the system because the earth is involved in that system. So if we take out the earth and then we're saying the ball only is a system, my system is no longer isolated, because when the ball falls, there's another external force that's it's caused by the earth. So that force caused the object to fall. It's attracting the object. If you now have earth here, you just have this earth, and then if this is the earth, and then here you have an object, then you are saying this is your system. This is your system only. What's causing this object to fall is external force that's not inside the system. So that force is not inside the system. So we're saying that the system is not isolated. But if we consider also the earth, the system, the force that caused the object to fall also come from the system. So therefore, we're saying that that system is isolated. It's isolated. We have no external force, outside force that's acting in the system. So that's an isolated system. No external forces. No external forces acting up. Forces acting up. So we have no external forces. So that's how you can do the isolated system. So this is the conservation of energy. So in an isolated system, the total energy remains the same. As the energy that we are going to talk about here is kinetic energy and the gravitational potential energy.